Let's do some quick example problems from this. And I'll possibly extend them a little bit as well as we go through. So, first of all, work out the average velocity for each stage of the journey. So we've got to look at the journey. This is often you may have to draw this. They may give you the information and they may say things like cyclist moves to a point A, which is 5 kilometres from home, takes them 20 minutes to get there. Could be going uphill or something. They stay there for 30 minutes and then return home downhill, and it only takes them 15 minutes. That's the sort of longer description they might give. So they might say things like cyclist, sorry, change the pen, cyclist cycles uphill or goes uphill 5 kilometres and it takes 20 minutes. They rest for 30 minutes and return home in 15 minutes. So that's the sort of minimal information they might give you to give you this graph. So a cyclist goes uphill for 5 kilometres and takes 20 minutes. So at 20 minutes, plot the point 5. They rest for 30 minutes, well, an extra 30 minutes then without movement. Displacement stays the same. And then it takes them 15 minutes to displace back to the start. So they're not going somewhere else. If they were going somewhere else, it would go off up here. But if they're coming back to their starting point, it comes down. And it's important you realise the return leads to a downward displacement. Okay, so we'll start off with our journey home, which is the origin. So part A, we've got 3 sections. Do label which part of the journey you're talking about. OA, that's where I'm going from. Displacement, change in displacement was 5 kilometres. Change in time was 20 minutes. So the gradient of this line gives me the velocity. It's a distance in a time. So we've got the distance over time, and that is 0.25 kilometres per minute. If you notice in the question now, and this is where people often will lose a mark, you must give the answer in terms of kilometres per hour. So we need to turn this into hours. I'm going to quickly show you, remind you of my technique. Start with the measure. Kilometres per minutes. All I want to change is the minutes into hours, so put a minute on the top, change the hour on the bottom, and we're going to multiply by 60 minutes is 1 hour. So if I multiply that through, it gives me 15 kilometres per hour. Don't need to go through any other more complicated sections. That's exactly what they've got in their calculation. They just gloss over the fact the 60-minute bit. This is a little bit more expressive. We need to do the other two lengths. So AB, delta S is 0, T is 30. The deltas just means a change, and that's because we're not talking about the same time away. We're not talking about always starting from 0. So V equals 0 over 30, which is 0 kilometres per minute. And it doesn't matter if it's per minute, that's also the same as kilometres per hour. But be expressive, do tell them what's happening. B to C, which is strictly back to O. Change in displacement is we're now coming back 5 kilometres. 5 kilometres backwards, change in time is 15 minutes. So my velocity is minus 5 over 15, which is minus 0.3 recurring kilometers per minute. Again, do the conversion. Some of you please be careful, make sure you're doing that, or you put a line over it, it should be acceptable as well. Change that into per hour, so kilometers a minute over an hour, minutes to hours. So 60 minutes is 1 hour, and this gives me a final velocity of 20 kilometers per hour returning. So its speed is 20 kilometers an hour, and that was for each stage. If we want to do the velocity for the total journey, part B, average journey from 0 to C directly, delta S equals 0. We haven't gone anywhere, we've gone there and come back. Delta T is equal to 15 kilometers is 65 minutes. So the velocity is 0 over 65, which equals 0 kilometers per minute, average. This is where I was talking about. If you do the gradient to any point from the origin, that's your average speed. And that's not kilometers per hour. And that's velocity because of the displacement. If we want the average speed, we need to know how far did we travel altogether. So just stress that's velocity. Speed OC, we just want to know distance travel. So the distance travelled is the distance from OA, irrespective of direction, plus the distance AB, irrespective of distance, direction, and BC, irrespective of distance. Now, chapter 3, you'll see this is vector notation. This modulus means I don't care, I just want to know the size of it, I don't care which direction. So all these bars say is size, ignore direction. It's the modulus function. So OA is 5, AB we did nothing, BC we did 5. So that's 10 kilometres. Now for the journey we're including the still time. So the total time we had initially 20, AB was 30 and BC is 15, which is 65 minutes. So my average speed, irrespective of direction, is 10 over 65. 10 over 65. Which is 2/13 or 0.1534846 kilometers per minute. The reason I'm doing this is, remember, I want to change this into hours, and I'm not going to show the calculation again. So they take the value, kilometres per minute, multiplied by 60 over 1, because it's 60 minutes in an hour, turns that into kilometres per hour. So multiply that answer by 60, and the average speed is 9.2307. So approximately to 3 significant figures, 9.23 kilometres per hour. And that's a sensible size. You may even want to put the 1 in if you want afterwards. So that's where those speeds and distances come from. Okay, let's do a velocity problem. So the velocity problem, they're now giving us nothing but description, so we've got to be able to draw a diagram. Now, this does say sketch a speed time diagram to illustrate the motion of the particle. I'd probably draw it anyway as I'm interpreting the information. So a particle moves in a straight line. So the particle means there's going to be no air resistance. It's a small point-like thing. It accelerates uniformly, constant acceleration. That's all we're worried about from the rest. So constant ac. The particle moves, no air resistance. Remember, you still need to be able to identify what these things mean. At rest, so initially u equals 0, u, initial velocity. Velocity is 8 t seconds. So I know my velocity axis needs to go from 0 to 8 at the moment. Particle travels at constant velocity for 5 t seconds. We don't know how long, so this is a complex problem. And because of the way that this works, we can't easily do this with Suvac equations. It's easiest to solve this problem if we draw a graph. The particle then accelerates uniformly to rest over a further 40 seconds. So I've got t here, 5t here, so that means overall we've got 6t and 40 seconds. We're going to have to make up an axis and hope the time bar is reasonable. And as long as it's reasonable, they will give us solutions. So we start at 0, 2, 4, 6, 8. As well, use the squares. And we're going across here, time. Diagrams, don't make them tiny. Make the diagrams reasonably big, like even using half the width of an A4 page here. That's even a bit small. You've got space, there's plenty of space in all the exam questions. Use space. Okay. So use space. Written in space for diagrams. We're not trying to save the paper. The paper's already going to be used up. It needs to be big and clear. Okay. Use the space. So, first section we've got is t seconds. So, use 2 squares for meaning t. We get to here. 5t, so that's 1, 2, 3, 4, 5. So that's 5t more, which gets us up to the point where we've got 6t. We haven't travelled anywhere. And then it takes 40 seconds to come back to rest. So that's some arbitrary number where we know this distance is 40 seconds. We don't know what the ending time is at the moment. T is 5, T there. It's often wise, if you're doing sketches, to be clear where the points are. And you should make sure the axes are labelled 8 meters per second, even if you've got to label them with vowels. So that's my diagram. T seconds, I've got velocity in meters per second. That's part A done, and that is part of my solving the problem. I wouldn't necessarily even have read what this is. Given the total displacement of the particle is 600 meters, So for part B, I'm going to write it over on this side so it stays together. What they're saying is displacement, our displacement on a velocity time graph. Well, the velocity is the gradient of a displacement time graph. The reverse of that is calculate the area. So that we need to know the area under the curve, or the graph, for the region they're saying. So they say the total displacement, the whole of this area, is 600 meters. Let's just see if we can get a highlighter pen. Come on. It's not letting me do the highlighter for some reason. Let's do it. Yeah, we'll use the space again. So this whole area, including that bit, all of that, 600 meters. By the way, do not use this sort of fancy pen in any exam. Black ink is preferred because it photocopies well. So displacement is the area under the graph. And now look at this and go, well, we haven't done solid effect formula, so that's not the case. It's a geometric problem. What shape is it? Shape is a trapezium. So we can do the formula for the area of a trapezium. So A is 1/2 perpendicular height and the lengths of the parallel sides. So we'll look which way round is it. My parallel sides, let's label it up. There's A, there's B, perpendicular height is that value there. So I can now put in my displacement. 600 is the area, and that's 1/2 times my perpendicular height, the 8, times the 2 parallel sides. So the first one's easy, that's 5t. B is 6t plus 40. So that's A, that's B. Expand, simplify the brackets. So we've got 44t plus 160 is 600. So 44t is going to be 440. So t is 10 seconds. Common follow-up to this sort of thing is, what would the acceleration be? So the acceleration is the change in velocity over the change in time. It's the gradient of a vt. So the acceleration for this part would be, what's the distance? 8 meters per second, divided by 10. Yes, we're in the same units. So it's 0.8 meters per second squared. Okay, I do write mixtures here of these S's. The reason mainly being I don't like this S getting mixed up with the displacement S. So if I'm talking about it being units and it's a unit on its own, I normally write S as seconds. If I'm doing velocities or accelerations, because it's along with a meter, it's clearly not going to be the S that's in the formula. Okay, so that's how we do those questions. Yeah, that's the first part. That's the sections all the way up to. I think you can even look at 2C. Let's just have a look at 2C. Let's just do a quick question that I'm going to make.